Hello everyone. This is the first presentation in this playlist regarding Ojaroudi's electromagnetic consciousness theory. The purpose of this introductory video is to present the general structure of the theory, to outline its main hypotheses, and to summarize the central claims, proofs, and supporting evidence. This video should be understood as an extended abstract of the full theory. All mathematical derivations, numerical simulations, and experimental analyses will be discussed in detail in the subsequent videos of this playlist. Ojaroudi's electromagnetic consciousness theory is built upon three main hypotheses, which are logically sequential and physically coupled. Hypothesis 1. There exists an electromagnetic interference pattern inside the brain. Hypothesis 2. Endogenous neural electromagnetic activity generates an inward electromagnetic gauge field, described by AU1 symmetry. Hypothesis 3. Consciousness emerges as a dressed electromagnetic gauge field, resulting from the interaction between U1 electromagnetic fields and SU2 neural gauge dynamics. Together, these hypotheses form a unified physical framework rather than independent assumptions. This slide highlights the originality of hypotheses 1 and 2 by demonstrating a bidirectional interaction between neural activity and electromagnetic fields. Neural activity in the brain generates electromagnetic fields, which can be measured externally. This is evidenced by EEG, which records electric signals produced by synchronized neuronal activity, and MEG, which measures the corresponding magnetic fields. At the same time, the interaction is not one-way. Electromagnetic fields applied externally can causally modulate neural activity. This is demonstrated experimentally by transcranial magnetic stimulation, where magnetic pulses induce cortical currents, by TDCS and TACS, where electric fields modulate neuronal excitability, and by electromagnetic deep brain stimulation, which targets deeper neural structures non-invasively. Together, these results establish a closed-loop interaction. Neural networks generate electromagnetic fields, and electromagnetic fields, in turn, influence neural networks. This bidirectional coupling forms the physical basis for hypotheses 1 and 2. This slide presents hypothesis 1, which states that there is an electromagnetic interference pattern inside the brain. The first proof comes from electrophysiology. Signals measured outside the brain using EEG are low frequency, while signals measured inside the brain using local field potentials reach frequencies up to 1,000 times higher. This strong frequency amplification indicates that high-frequency electromagnetic fields and waves exist inside brain tissue, not just slow electrical signals. The second proof comes from Valinsky's theoretical work, which shows that neural activity operating in this frequency range necessarily generates electromagnetic waves inside the brain. Once electromagnetic waves exist, they must propagate. The figures on the right illustrate the trajectory of electromagnetic waves inside the brain, following cortical geometry. Together, these results establish the physical basis for wave propagation inside the brain, which is a necessary condition for electromagnetic interference patterns. In the continuing proof for hypothesis 1, we now consider the boundary conditions of the brain that govern electromagnetic wave propagation. Proof 3 is based on the frequency-dependent behavior of brain tissues. At high frequencies, cerebrospinal fluid behaves effectively like a perfect electric conductor, reflecting electromagnetic waves inward. At low frequencies, the skull acts as a strong attenuator or conductive reflector. Together, these properties confine electromagnetic waves inside the cranial cavity. On the left side of the slide, the videos show electromagnetic wave propagation inside an elliptical perfect boundary, demonstrating inward reflection and confinement of the field. Proof 4 follows directly from this confinement. When electromagnetic waves are fully reflected inward, constructive and destructive superposition becomes unavoidable. This produces stable hot spots and cold spots in the electromagnetic field distribution. On the right side, the brain wave trajectory visualized in the cortex, based on Valinsky's work, illustrates how propagating neural electromagnetic waves follow structured paths and naturally form interference patterns. Together, these two proofs demonstrate that the brain necessarily supports a dynamic electromagnetic interference pattern, completing the physical validation of Hypothesis 1. In the continuous proof for Hypothesis 1, we now bring together the 4 independent physical evidences showing that an electromagnetic interference pattern exists inside the brain. First, we observe a strong frequency amplification from outside to inside the brain. EEG signals recorded at the scalp remain in the low-frequency range, while intracranial signals measured as local field potentials reach frequencies up to 1,000 times higher. This frequency intensification directly implies the presence of high-frequency electromagnetic fields propagating inside brain tissue, not merely passive electrical recordings. Second, Galinsky simulations demonstrate that neural activity operating in this frequency regime necessarily generates electromagnetic waves inside the brain. The trajectories shown here are not conceptual illustrations, they are computed EM wave paths within cortical geometry, confirming real wave propagation rather than static fields. Third, the brain's internal boundary conditions enforce inward reflection. At high frequencies, the cerebrospinal fluid behaves as a conductive reflective layer, effectively acting like a perfect electric conductor, while at low frequencies the skull functions as an attenuator or conductive reflector. Together, these layers form an electromagnetic cavity that reflects waves back into the brain volume. Finally, with fully reflected inward waves, constructive and destructive superposition becomes unavoidable. This produces stable electromagnetic hotspots and cold spots, which are the physical signature of an interference pattern inside the brain, as shown here. Taken together, these 4 proofs establish Hypothesis 1. The brain does not merely generate electromagnetic activity, it supports structured electromagnetic interference patterns within its own geometry. More detailed derivations and simulations are presented in Part 1 of this playlist. We now move to Hypothesis 2. Hypothesis 2 states that endogenous neural electromagnetic activity organizes into an inward electromagnetic gauge field with U1 symmetry. The first proof shows that neural and biophotonic sources generate electromagnetic waves with well-defined amplitudes and phases. These waves superpose to form a total electromagnetic field tensor, whose interference patterns act as functional computational structures inside the brain. Through constructive interference, localized electromagnetic hotspots emerge, and changes in these fields propagate across distant regions, demonstrating functional non-locality. This behavior is consistent with a coherent inward-directed U1 gauge field, rather than isolated local emissions. The second proof links these electromagnetic structures directly to brain functionality. Interference patterns correlate with activity in Wernicke's area, the medial temporal lobe, and Broca's area during language, memory integration, and decision-making. Coherent electromagnetic flow converges inward, forming dynamic canonical focal points that synchronize distant brain regions. These focal points act as computational hubs, integrating information beyond synaptic wiring alone. Together, these results show that endogenous neural electromagnetic activity self-organizes into an inward, coherent U1 electromagnetic gauge field, supporting large-scale integration and cognition. Further mathematical formulation and simulations are presented in Part 2 of this playlist. We now arrive at the main body of the theory. Up to this point, Hypothesis 1 established the existence of electromagnetic interference patterns inside the brain, and Hypothesis 2 showed that endogenous neural activity organizes these patterns into an inward U1 electromagnetic gauge field. Here, Hypothesis 3 builds directly on those results. We now dive into the proposed theory through a concrete example. The problem we aim to solve is the following: how corticothalamic neural pathway dynamics can be modeled using a dressed gauge field framework combining U1 and SU2. On the left, we start from biological reality. Corticothalamic circuits, including cortex, thalamus, basal ganglia, and their direct and indirect pathways, exhibit strong oscillatory dynamics, governed by excitation-inhibition balance. These biological oscillations are the starting point of the model. Next, we move to a coarse-grained theoretical description. Neural populations are represented as an SU2 neural gauge network, capturing information dynamics, competition, and coupling between neural states. At this stage, the system exhibits non-zero SU2 curvature, corresponding to unstable or competing neural trajectories. Now comes the key step of the theory. The endogenous U1 electromagnetic field, generated by neural activity and demonstrated in hypotheses 1 and 2, couples to this SU2 network. This electromagnetic coupling acts as a stabilizing mechanism. Through feedback and feed-forward interaction between SU2 neural dynamics and the U1 electromagnetic field, the curvature is progressively reduced. As curvature stabilizes, the system transitions into phase-locked corticothalamic oscillations. These stable oscillations are directly observable in EEG and MEG measurements, providing an experimental signature of the model. In summary, biological oscillations generate SU2 neural curvature. U1 electromagnetic coupling stabilizes this curvature, leading to coherent, stable corticothalamic oscillations. This stepwise process forms the core mathematical mechanism of the dressed gauge field theory of consciousness. We now identify the concrete problem addressed by the theory. Corticothalamic neural pathways exhibit competing direct and indirect loops, particularly within the basal ganglia thalamocortical system. These competing excitatory and inhibitory pathways generate unstable neural firing and oscillatory conflicts, which are clearly observed in biological recordings. Traditional neuron-level models describe these pathways anatomically, but they do not explain how global stability, coherence, and selection emerge dynamically. This is the gap the dressed gauge field framework is designed to address. Step 1 starts from biology. Here we see direct and indirect corticothalamic pathways operating simultaneously. The cortex drives both pathways, producing competing oscillatory modes. These feedback loops naturally generate instability, phase competition, and oscillatory divergence, which is the real biological problem observed in neural firing data. In step 2, the biological network is coarse-grained. Neural populations are mapped onto a coarse SU2 gauge network, where nodes represent population states. Links represent excitatory and inhibitory couplings. This abstraction preserves biological meaning while allowing us to define loop holonomy and gauge curvature, which cannot be done at the single neuron level. Step 3 reveals the key instability. Because the direct and indirect pathways do not commute, the closed loops in the SU2 network generate non-zero gauge curvature. This non-zero curvature corresponds to unstable oscillatory regimes, exactly matching pathological or conflicted corticothalamic activity. At this stage, the system is dynamically rich but not yet stable. We now continue from step 3, where the core difficulty in corticothalamic dynamics becomes explicit. In step 3, the competing direct and indirect corticothalamic pathways are represented as a coarse-grained SU2 gauge network. Because these pathways do not commute, their closed loops generate a non-zero SU2 curvature. Physically, this corresponds to unstable neural oscillations, competing firing patterns, and fluctuating cortical thalamic activity, as observed in EEG and LFP signals. In step 4, the endogenous U1 electromagnetic field couples to this SU2 network. Electromagnetic gradients act as a damping field, smoothing phase differences across the network. Mathematically, the U1 field reduces SU2 curvature by acting on the plaquette structure of the gauge loops, introducing coherence and phase alignment. As this electromagnetic damping continues, the system evolves toward a stable, zero curvature SU2 fixed point. At this point, competing loops no longer generate conflict. Instead, the corticothalamic network settles into a coherent, phase-locked oscillatory state, driven by the U1 electromagnetic field. In the final step, this zero curvature SU2 fixed point is interpreted biologically. It corresponds to stable corticothalamic oscillations, balanced direct and indirect pathways, and coherent neural population dynamics. These stabilized oscillations are directly observable in EEG and MEG recordings. This example shows how a real biological problem, unstable corticothalamic dynamics, is naturally resolved by the proposed dressed gauge field framework, through the interaction of SU, 2, neural dynamics and the U, 1, electromagnetic field. For a deeper mathematical treatment, simulations, and additional examples, we invite you to explore the other videos in this playlist, which fully develop and discuss Ojaroudi's electromagnetic consciousness theory.